Welcome! In this session, we'll dive into problem number 1533, find the index of the large integer. This problem challenges us to efficiently determine the index of the largest element in a hidden array using an API-based approach. Let's explore the problem step by step, analyze different strategies, and uncover the most optimal solution. Let's get started. In this problem, you are tasked with finding the index of the largest element in a hidden array. The array is not directly accessible to you, but you are provided with an API called ArrayReader that allows you to compare the sums of two subarrays. The ArrayReader.compare submethod takes four parameters, L1 and R1, which define the indices of the first subarray, and L2 and R2, which define the indices of the second subarray. It returns 1 if the sum of the first subarray is greater, -1 if the sum of the second subarray is greater, and 0 if the sums are equal. Importantly, the largest element in the array is guaranteed to be unique, and your goal is to determine its index using this API. The length of the array, n, is provided as input and can range from 1 to 100,000. The output of this problem is the index of the largest element in the hidden array, which is 0-based. Let's look at a few examples to better understand the problem. In the first example, the hidden array is 1, 7, 3, 6, 5, 2, and the length of the array is n equals 6. The largest element in this array is 7, which is located at index 1. Therefore, the output is 1. In the second example, the hidden array is 4, 2, 1, 5, 3, with n equals 5. Here, the largest element is 5, which is found at index 3. So, the output is 3. Now, let's discuss a third example to further clarify. When the hidden array contains only one element, as in n equals 1 with hidden equals 10, the single element is the largest by default. Its index is 0, so the output is 0. Finally, we have to keep in mind some constraints. The length of the array, n, can go up to 100,000, and all elements of the array are integers within the range of -10⁻9 to 10⁻9. Additionally, the largest element is guaranteed to be unique, which ensures there is no ambiguity in the output. There are a few edge cases to consider while solving this problem. First, if the array contains only one element, the solution is straightforward as that element is the largest. For arrays with two elements, a single call to the API is sufficient to determine the larger element. For large arrays, efficiency is critical, and the solution must work within O log n API calls. The array may include negative numbers, but the approach to finding the largest index remains unchanged. Finally, even if the array has repeated values, the guarantee that the largest value is unique ensures there will always be a clear result. These considerations will guide us in designing an efficient and robust solution using the ArrayReader API. To tackle this problem, let's first consider the brute force approach. The idea here is straightforward. Iterate through each index of the hidden array and use the CompareSub API to compare subsets of elements. Essentially, for every index, we compare it with others until we find the one that contains the larger integer. While this might seem intuitive, the implementation uses nested loops, leading to a time complexity of O(n squared). Each call to CompareSub involves summing up elements, which takes O(n), and since we might call it up to O(n) times, the cost becomes prohibitive for larger arrays. Moreover, the space complexity is O(1), as it doesn't require additional storage. However, the inefficiency of this approach becomes clear for larger values of n, such as 10 to the power of 4 or beyond, making it impractical for competitive programming. To improve, we need to leverage the constraints and properties of the problem. This brings us to the binary search approach. Binary search provides a more efficient strategy by reducing the search space in a systematic way. The problem guarantees that one index contains a strictly larger integer, allowing us to use this property effectively. The idea is to divide the array into two halves and use CompareSub to determine which half contains the larger integer. If the sum of elements in the left half is greater, we narrow our focus to that half, otherwise, we look at the right half. This process is repeated until we isolate the index of the larger integer. The time complexity of this approach is O log n, as the range is halved with each step, though the summation within CompareSub still incurs an O(n) cost per call. The space complexity remains O(1), as no additional storage is required. This method is highly efficient even for large input sizes. However, one drawback is that the summation in CompareSub can still be costly for very large n. To address this, we introduce an optimized version of binary search with caching. The optimized binary search approach builds on the standard binary search by adding caching to reduce redundant computations. The key insight here is to store the results of CompareSub calls in a cache. Before making a new API call, we check if the same subset comparison has already been performed. If so, we use the cached result instead of recomputing it. This optimization maintains the log n time complexity of binary search, while reducing the overhead associated with summing subsets. The space complexity increases to n due to the cache, but this is a worthwhile trade-off for the performance gains achieved by avoiding redundant work. Ultimately, this approach is chosen because it balances time and space complexity effectively. Brute force is ruled out due to its inefficiency, and while standard binary search is a solid improvement, caching further enhances performance. By combining binary search with caching, we minimize API calls and ensure efficient handling of even the largest inputs, making it the most practical strategy for this problem. To solve this problem, we start by understanding the task at hand. We are working with a hidden array, and we cannot access its values directly. Instead, we are provided with an API called CompareSub, which allows us to compare the sums of two subarrays. Our goal is to determine the index of the largest element in this hidden array. Now, the key idea here is to use the CompareSub API iteratively. By carefully comparing the sums of subsets of the array, we can infer which index corresponds to the largest element. To begin, we initialize a variable n to represent the length of the hidden array. If the length isn't explicitly provided, we will need to determine it. Additionally, we set a variable max_index to track the index of the largest element. Initially, we assume max_index is 0, meaning the first element is the largest until proven otherwise. With our initial setup complete, the next step is to iterate through the array. Using a loop, we go through each element starting from index 1 up to n1. In each iteration, we compare the current max_index with the current element at index I. This is achieved by calling the CompareSub API. Specifically, we use the API to compare two subarrays, one that includes the element at max_index and another that isolates the element at index I. Based on the result of this API call, we make a decision. If the sum of the first subarray is greater, it means the current max_index still holds the largest value, and we continue without making any changes. However, if the second subarray is larger, it indicates that the element at index I is greater, and we update max_index to I. We also need to account for edge cases, such as when the array has only one element, in which case we directly return index 0, or when the array contains duplicate elements. In the latter scenario, the algorithm will still identify one valid index corresponding to the maximum value. Once the loop finishes, the value stored in max_index will represent the index of the largest element in the array. At this point, we simply return max_index as the result. Now, let's consider why this approach is effective. The CompareSub API is a powerful tool that allows us to compare sums of subarrays without directly accessing the array elements. By isolating one element at a time in these comparisons, we can systematically identify the largest number. This algorithm is also efficient. Since we make one API call for each of the n1 comparisons, the time complexity is linear, or n. Moreover, because we avoid accessing the array directly, we comply with the problem constraints while still achieving our goal. One important detail to highlight is how the algorithm handles ties. If two elements are equal, the algorithm will always select the first occurrence. This is because the max_index variable is updated only when a strictly larger value is found. This ensures consistency in the output. Additionally, the algorithm is straightforward in its use of data structures. We don't require any complex structures, instead, we simply rely on a single variable, max_index, to track the largest value, and a loop to iterate through the indices. This simplicity results in minimal space usage, making the approach easy to implement and understand. To solidify our understanding, let's walk through an example. Imagine the hidden array contains 5 elements, 3, 8, 2, 8, 7. We start by initializing max_index to 0, corresponding to the first element. Next, we compare the element at index 0, which is 3, with the element at index 1, which is 8. Since 8 is larger, we update max_index to 1. Then, we compare the element at index 1, which is now our current maximum, with the element at index 2, which is 2. Since 8 is still larger, max_index remains unchanged. Moving forward, we compare the element at index 1 with the element at index 3. Both are equal to 8, so again, max_index stays the same. Finally, we compare the element at index 1 with the element at index 4, which is 7. Since 8 is greater than 7, there's no change to max_index. After completing all comparisons, we return max_index equals 1 as the index of the largest element in the array. This Python implementation solves the LeetCode problem number 1533, find the index of the large integer, using a binary search approach. The task is to find the index of the largest integer in a hidden array, and we interact with the array by calling an API compareSub that compares sums of two subarrays. ###explanation. 1. Initialization. The method getIndex starts by defining the search bounds left and right, which initially span the entire array, from index 0 to n1. 2. Binary search. The loop continues as long as left is less than right, meaning there are still multiple indices to consider. At each step, the midpoint mid is calculated as left plus right, //2. The sizes of the left and right halves are determined. The left half includes indices, left, mid, and the right half includes indices, mid plus 1, right. 3. Calling compareSub. The compareSub API is used to compare the sums of the left and right halves. If compareSub returns 1, the sum of the left half is greater, indicating the large integer lies in the left half. In this case, right is updated to mid to narrow the search to the left half. Otherwise, if compareSub returns -1, the sum of the right half is greater, so the large integer is in the right half. Left is updated to mid plus 1. For termination, when left equals right, the search converges to a single index, which is the position of the large integer. The method returns this index. This approach ensures efficient search with a time complexity of O log n, as the search space is halved in each iteration. The binary search strategy minimizes the number of compareSub calls, adhering to the problem's constraints. Here, we begin with the Java implementation of the problem. The primary goal is to locate the index of the largest integer in a hidden array using a binary search approach paired with the provided compareSub API. First, we define the getIndex method, which takes two parameters, n, the size of the hidden array, and compareSub, the API used to compare sums of subarrays. Inside the method, we initialize two pointers, left and right, to define the search boundaries. Initially, left is set to 0, and right is set to n1, representing the entire array. The main logic is implemented using a while loop, which runs as long as left is less than right. Within the loop, we calculate the midpoint between the current left and right boundaries using integer division. The compareSub API is then called to compare the sums of two subarrays, one from left to mid, and the other from mid plus 1 to right. The result of this comparison helps us determine which half contains the larger integer. If the result is 1, it means the left subarray has a greater sum, so we move our search boundary by updating right to mid. On the other hand, if the comparison result is not 1, it means the right subarray has a greater sum. In this case, we adjust the search boundary by updating left to mid plus 1. This process continues, narrowing down the search range until left equals right. At this point, the loop terminates, and left represents the index of the large integer. The method then returns this index as the result. Finally, we define the compareSub API interface, which specifies the functionality of the compareSub method. This method takes four parameters representing the start and end indices of two subarrays, L1 and R1 for the first subarray, and L2 and R2 for the second subarray. It returns 1 if the sum of the first subarray is greater, -1 if the second subarray's sum is greater. This interface is crucial for interacting with the problem's hidden array, ensuring our solution adheres to the constraints of the problem. To solve the problem of finding the index of the largest integer in a hidden array, we rely on the compareSub API. This function allows us to compare the sums of two subarrays and returns 1 if the first subarray's sum is greater, -1 if the second subarray's sum is greater, or 0 if the sums are equal. Using this API, we can implement a binary search algorithm to efficiently locate the largest integer. By narrowing down the range based on the results of compare sub, we can pinpoint the index of the desired element step by step. Let's walk through the solution with detailed examples to understand how this approach works in practice. In the first example, we have a hidden array of size 5 with the values 1, 2, 5, 2, 1, where the largest integer is at index 2. We start by initializing left to 0 and right to 4, covering the entire array. During the first iteration, we calculate mid as 0 plus 4, //2, which gives us 2. Using the compare sub API, we compare the sum of the left half, 1, 2, 5, with the sum of the right half, 2, 1. The left half has a sum of 8, while the right half sums to 3. Since the compare sub result is 1, indicating the left half is greater, we update right to mid, narrowing our range to indices 0 through 2. In the second iteration, the range is now limited to indices 0 through 2. We calculate mid as 0 plus 2, //2, which results in 1. Using the compare sub API again, we compare the sum of the left half, 1, 2, with the sum of the right half, 5. The left half sums to 3, while the right half sums to 5. Since the compare sub result is -1, indicating the right half is greater, we update left to mid plus 1, setting it to 2. At this point, left and right both point to 2, so we terminate the search. The largest integer is located at index 2. In the second example, we have a hidden array of size 4 with the values 3, 1, 6, 2, where the largest integer is at index 2. We initialize left to 0 and right to 3. In the first iteration, we calculate mid as 0 plus 3, //2, which equals 1. Using the compare sub API, we compare the sum of the left half, 3, 1, with the sum of the right half, 6, 2. The left half sums to 4, while the right half sums to 8. Since the compare sub result is -1, indicating the right half is greater, we update left to mid plus 1, setting it to 2. With left and right both pointing to 2, we terminate. The largest integer is at index 2. In the third example, we have a hidden array of size 6 with the values 1, 3, 4, 6, 5, 2, where the largest integer is at index 3. We start with left set to 0 and right set to 5. In the first iteration, we calculate mid as 0 plus 5, //2, which equals 2. Using the compare sub API, we compare the sum of the left half, 1, 3, 4, with the sum of the right half, 6, 5, 2. The left half sums to 8, while the right half sums to 13. Since the compare sub result is -1, indicating the right half is greater, we update left to mid plus 1, setting it to 3. With the range now reduced to indices 3 through 5, we proceed to the second iteration, calculating mid as 3 plus 5, //2, which gives us 4. Using compare sub, we compare the sum of the left half, 6, 5, with the sum of the right half, 2. The left half sums to 11, while the right half sums to 2. Since the compare sub result is 1, indicating the left half is greater, we update right to mid, narrowing the range to indices 3 through 4. In the third iteration, we calculate mid as 3 plus 4, //2, which equals 3. Comparing the left half, 6, to the right half, 5, using compare sub, we find the left half is greater, so we update right to mid, setting it to 3. At this point, left and right both point to 3, so the largest integer is at index 3. The time complexity of our solution is O log n, and this is because the algorithm utilizes a binary search approach to pinpoint the index of the largest integer within the hidden array. At the start of each iteration, the range defined by left and right is divided approximately in half, with the midpoint calculated as left plus right, //2. The compare sub function is then used to compare the sums of two halves of the current range. Importantly, this comparison operation takes constant time, O1, because the underlying API handles the sum computation without explicitly iterating through the hidden array. Based on the result of compare sub, the algorithm decides whether to narrow the search to the left or right half by updating the left or right pointers. This halving process continues until the range is reduced to a single element. Since the size of the range is halved in every iteration, this requires approximately log base 2 of n iterations. Mathematically, the range starts at size n, then reduces to n/2, then n/4, and so on, until it becomes 1. With each iteration performing only O(1) work due to the single compare subcall, the total time complexity of the algorithm is O log n. The space complexity of the solution is O(1), meaning it uses a constant amount of extra memory. This is because the algorithm only requires a few variables, such as left, right, mid, left_size, right_size, and comparison, to manage the search process. No additional data structures, such as arrays or lists, are utilized, and there are no recursive calls that would add to the memory overhead. The CompareSub API operates externally on the hidden array, so its memory usage is not included in the algorithm's space complexity. Breaking it down further, the memory required for variables remains constant regardless of the size of the array, and since there are no dynamic data structures or recursion involved, the overall space complexity remains O(1). This efficiency in memory usage complements the algorithm's optimized time complexity, making it highly suitable for the problem's constraints. When comparing the optimized binary search approach to a brute force method, the differences in efficiency become clear. A naive brute force approach would involve iterating through the entire hidden array to find the largest integer. This would result in a time complexity of O(n), as each of the n elements would need to be examined. However, the space complexity would still be O(1), since no additional memory would be required. In contrast, the optimized approach drastically reduces the time complexity to O log n, by leveraging the binary search strategy and the CompareSub API to minimize the number of comparisons required. The key advantage of binary search is that it repeatedly halves the search range, which minimizes the number of CompareSub calls, a critical constraint in this problem. With the search range halving at each step, the logarithmic time complexity is the most efficient solution possible, given the constraints. The space complexity of O(1) is maintained, as no extra memory is used. In conclusion, the optimized approach is significantly faster than brute force while adhering to the problem's constraints, making it the ideal solution with a time complexity of O log n and space complexity of O(1). When tackling this problem, there are a few common mistakes to watch out for. First, misusing the API or functionality provided, such as CompareSub, can lead to issues. It's crucial to understand how the function operates, including its constraints, and ensure that subarray indices are always valid and within bounds. Errors like off-by-one mistakes or invalid indices can result in runtime errors or incorrect comparisons. Another frequent pitfall is overlooking edge cases. Scenarios like empty arrays, single-element arrays, or arrays where all elements are identical often trip up solutions that are designed only for generic cases. These edge cases are critical to handle because interview test cases usually include them. Brute force approaches, while sometimes helpful in clarifying the problem, can also become problematic. If you rely on brute force without optimizing it, you might run into time limit exceeded errors, especially for larger constraints like n greater than 10,000. Finally, ignoring problem constraints can lead to unnecessarily complex solutions. Constraints, such as sorted arrays or unique values, often provide hints for simplification. Missing these opportunities can make your solution more complicated than it needs to be, wasting time and effort. Another mistake to avoid is overcomplicating the solution. Adding unnecessary steps or overthinking the problem can lead to convoluted code that's harder to debug and explain. Simpler, more direct solutions are generally preferred, especially in interviews, as they minimize errors and improve clarity. In terms of interview strategies, it's essential to take the time to fully understand the problem statement and any provided APIs. If anything is unclear, don't hesitate to ask the interviewer for examples or clarifications. Constraints are another tool you should use to your advantage. They often hint at the optimal approach, such as steering you away from O(n)² solutions when n is large. While brute force can be a helpful starting point for brainstorming, you should aim to discuss and implement a more optimized solution as soon as possible. Clear communication is also key. Talk through your thought process with the interviewer, especially when weighing different approaches. Highlight the trade-offs in terms of complexity and readability. Finally, always verify your solution with edge cases, such as the smallest or largest possible inputs, duplicates, and any other extremes, to ensure your code is robust. This problem is closely related to several others on LeetCode that you might find helpful to review. For example, LeetCode 33, Search and Rotated Sorted Array, emphasizes the use of binary search and leveraging constraints to narrow down the solution. LeetCode 153, Find Minimum and Rotated Sorted Array, similarly focuses on understanding array properties to optimize the solution. Another example, LeetCode 875, Cocoa Eating Bananas, illustrates binary search on answers, which is a useful technique for efficiently solving problems with APIs. Finally, LeetCode 1011, Capacity to Ship Packages Within D-Days, deals with splitting arrays and optimizing comparisons. In terms of alternative approaches, one option is divide and conquer. Instead of relying on brute force, you can recursively divide the array into smaller parts, using the API to make efficient comparisons. This method is particularly useful for large inputs, though it may be more challenging to implement correctly. Another powerful strategy is binary search. By narrowing down the solution space using ordered evaluations, you can solve the problem efficiently, provided you have a clear understanding of how to set up the binary search conditions. Another approach to consider is the sliding window or two-pointer technique. This method is particularly useful for optimizing subarray comparisons, especially when the problem involves continuous subarrays. By maintaining a dynamic window or adjusting pointers, you can significantly reduce the computational overhead compared to brute force. However, this approach may be less intuitive for problems that involve discrete or more complex comparisons, so it's important to assess whether it's the right fit for the specific problem. Ultimately, the key takeaway is to choose the approach that best aligns with the problem's constraints and requirements, balancing efficiency with clarity in your implementation. Great job! We've successfully tackled the problem Find the index of the large integer. Remember, understanding the problem constraints and efficiently using APIs are key to solving such challenges. Thank you for watching, and don't forget to like, share, and subscribe for more problem-solving content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!